I actually built a clay and straw house in Ottawa near the Civic Hospital. So kind of in the experimental farm area. And I'm a part-time professor at Algonquin, and this is a type of lecture that I give a lot. And it gives kind of a background in, I guess a movement that started a long time ago that has, well, revolutionized the way I think about buildings as a licensed architect, and where I wish more of our industry would go. So I'll start off. Nature is the gold standard, building biology. My name is Bobby Ilg. I graduated from the U of M 2000, Carleton University in 2005. I'm also a part-time professor at Algonquin College in the Bachelor of Interior Design program. I'm the principal architect at our architecture, it's kind of design build now, firm in Ottawa called Build Well to Be Well. I discovered building biology about 7-8 years ago now. It's about designing nature-based homes using the principles of building biology, which are a series of 25 principles, which we'll be going through shortly. I got the first building permit for a natural building in Ottawa, and I'm very happy to say there have been additional natural buildings built in the Ottawa area since. So it opened the city of Ottawa to other alternative methods of building. And I got my building permit very smoothly, so it was nice to see that things are moving toward being open enough to consider these. We do clay straw homes. We have about 5 projects this year, a lot of them in Ottawa and some just on the outskirts. We do a panelized system, which I'll describe in a little more detail as we go. And I continue to evolve the panel systems and the panels. These are some of our wall panels that went into our construction on our job site. So building biology recognizes that nature is the gold standard for a healthy human environment and the ultimate model for perpetual ecological balance. Building biology is unique on its emphasis on human health, with the perspective that there is almost always a direct correlation between the biological compatibility of any building material and its ecological performance. In other words, that which is truly healthy for us will also be healthy for the environment. A lot of our clients actually suffer from a condition known as multiple chemical sensitivities. So they reach out to us. We do some consultation work on there. That's what drew me a little bit into building biology. And as I dove into it, I realized they understood natural buildings in a way that I could appreciate. So it's the first ecological building movement. It started in Germany shortly after World War II. And it developed as a series of professionals. We're talking doctors, chemists, builders, natural builders of all sorts, that started to look at widespread illness in building failure related to a lot of the new buildings that went up after World War II. They were also seeing some signs that this same building illness wasn't necessarily occurring in some of their older structures. And of course, they had several to look at. So it started off as Dr. Anton Schneider founded an interdisciplinary working group of the Healthy Building Living in 1969. It turned into building biology in about the mid-70s, and Helmut Sehe had brought it to North America in '87. Essentially, he translated the German text to English so that more people could partake. Right now, there's building biology institutes in most of the continents across the world, so it is pretty well known now. And you know, it's a series of experts, architects, planners, wood scientists, medical professionals, and I've appreciated the amount of sharing that actually occurs as becoming a building biology, a building biologist. And part of that process was the understanding that when I went to a lot of my lectures, a lot of the people who were there were looking for answers because they were suffering from chemical sensitivities or other building-related illnesses. And I was the only architect. After going through it, I would say I wish every architect and every designer had the, that it was more integrated into universities and colleges. And a big reason I brought it into our interior design program at Algonquin College. So I'll go through the 25 principles and then get into a little bit of the building science side of it and why natural buildings work the way they do. So site and community design. Verify that the site is free of naturally occurring health hazards. What you see there on the photo is a cancerous growth on a tree. And this can happen from radon levels or anything else coming through the earth through the path lines that are there. Another one, place dwellings. So occupants are undisturbed by sources of man-made air, soil, water, noise, and electro pollution. Very difficult to do in a city, but we try our best. Place dwellings in well-planned communities that provide ample access to fresh air, sunshine, and nature. The photo that you see there is actually a planned community in Santa Fe, New Mexico. There's a lot of people living in this very dense area, but the idea is to have as much green space as built space. And it's actually a very beautiful place to go visit, and it creates that community aspect for everyone who lives there, because they are encouraged not to have streets, but pathways where they're walking and interacting with one another. And plan homes and developments considering the needs of community, families, and individuals of all ages. I always looked at the community design and the community aspect of the building biology principles, as nice, but I didn't really focus on their importance until quite recently. It was largely with the pandemic. Community is, I think, the base of everything when it comes to the natural environment and how we want to work in the environment or with the environment. It won't happen without community. So, I do appreciate these first four, principles on a much different level now. Occupant health and well-being. Use natural, unadulterated building materials. I don't know if you can see in that photo, but there's some sprouting. That's a clay and straw wall as it's drying. To give you some base, a clay and straw wall that's even 3.5 inches thick, it's, let's say, a 4-foot wide by 8-foot high panel will have about 200 gallons of water put into it during construction. Now, that's a lot of water. And the wall needs to dry itself out. And during that process, the little seeds inside the straw will actually start to sprout. And your wall is dry when those little green sprouts start to shrivel up, because the roots are actually helping the wall panel dry, and that's kind of when the inner core of your wall is beginning to fully dry, is when they dry up. So it's interesting how nature, helps each other with a process like the clay and straw. So allow natural self-regulation of indoor air humidity using hygroscopic high humidity buffering building materials. I'll get into that in a little bit later. That is one I do emphasize on. Assured low total moisture content and rapid desiccation of wet construction processes in new buildings. Like clay and straw, it needs to be dry. And if you can dry it, that wall panel that took in 200 gallons of water will be able to take on another 200 gallons of water because it dried itself out once already. And it's wild, like I've seen it, right? My own house, I left the walls exposed for 3 seasons. And you'll see photos of it, but it looked the day that we put it in after 3 full winters. And it's amazing the way clay will keep everything else in that wall system dry. But the key, making sure it dries out properly the first time. Designed for a climatically appropriate balance between thermal insulation and thermal storage capacity, or thermal mass. I'll talk about this a little bit further as well. Planned for climatically appropriate surface and air temperature. Again, how you heat becomes very important in the building biology discipline, and we primarily rely on radiant heat on all sources and forms. So I do emphasize that. What you see in the photo there is a masonry heater. Has anyone heard of a masonry heater before? No? A masonry heater is a big mass stone fireplace. What's interesting is that the fire you light is one big fire. It goes up a series of channels and it goes through the fireplace. It goes either through horizontal channels or vertical channels. It can go through a heated seat like you see here, and then eventually it goes up the chimney. I have one in my own house, and I did some infrared to show you later on in the diagram, but the masonry heater hits its hottest peak about 12 hours after the fire goes out. So with one fire a day, you heat up to 2,000 square feet. It's remarkable. You don't smell it because it's burning all the gases from the smoke the whole way through. And you see it at the very beginning, a little bit of smoke coming. After that, you just see little quivers. For myself in our house, it's amazing how the masonry heater becomes that central point. You could imagine a big stone mass, there's no fire, and the next morning it's its hottest peak. My kids resonate to it, and the heated seat is phenomenal. It's a really ancient way of heating, but still probably one of the best, and simply forgotten. Like, yeah, this is probably dates back to the medieval times. China and Mongolia were heating this way well over 1,000 years ago. And it's, pretty remarkable stuff. 10, provide for ample ventilation. As an architect, I know we've gotten into a lot of mechanical systems to provide fresh air. I'm a strong convert back to operable windows. Most of our buildings do not have nearly enough operable windows as far as I'm concerned. I've come full circle and don't quite realize why we use electricity and energy to bring in fresh air. It's as simple as opening a window. And when you get your cross ventilation and everything else, it is much better for your long-term health related to that interior environment. So I do appreciate this building biology principle because I think it's very critical to the way we live in our buildings and work in our buildings. So use appropriate thermal radiation strategies for heating buildings, including passive solar wherever viable. When you want to collect heat from the sun, you need something to store it. So that's where the thermal mass, that fine balance of insulation and mass is really critical, especially for a climate like we have in Ottawa, where you get a lot of cold months. Our house will be almost 5 degrees difference when the sun is out in the middle of winter. And we store a lot of that sunlight in our mass, both the floors and the walls. And it's remarkable how consistent the heat remains just by the sun coming out. Like, I turn on my heat in November, we turn it off probably end of April. And the swing months are really the sun doing its thing. And, I have not overindulged in the insulation side of things. It really is the mass working with the sun. So provide in abundance a well-balanced natural light and illumination while using color in accordance with nature. Provide adequate acoustical protection from harmful noise and vibration. Can't stress this enough. A natural clay, or especially clay or a lime plastered wall, will have a little bit of texture on it, and that controls all the reverberation in your house. So the acoustics on a mass wall are phenomenal. It really is once you live in it, it's hard to go back. I notice noises so much more now. And when you use radiant, quiet sources of heat and not forced air, it is really, you gain an appreciation for the silence that comes with it. Utilize non-toxic building materials that have neutral or pleasant natural scents. What you see here is a citrus thinner that is used actually of orange peel. So, you know, there are alternatives to what we have on the market today. And when you use natural materials, the big thing I have to stress is when you use natural finishes for natural materials, they will always last longer. And there's science behind it, right? But yeah, it's simply forgotten. The chemical industry has really devoured our industry in you know, building industry, and for whatever reason, that's all we tend to see. So, use appropriate water and moisture exclusion techniques to prevent interior growth of fungi, bacteria, dust, and allergens. Clay plaster, I'll be bringing this up a lot. Clay plaster controls majority of the humidity in our house. When we have a shower in our bathroom, the clay plaster will soak up all the humidity, so we don't have a steamed up mirror. We never have a steamed up mirror because the walls, the clay plaster on those walls, soak it up and then re-release it again when it gets drier in there. So it's amazing seeing stuff like that work. Wood, untreated wood, will do a lot of similar things. It doesn't have quite as much of that hygroscopic capability, but it will take in a lot of moisture. So yeah, just by putting natural materials in, you can control your humidity significantly. Assure best possible potable water quality by applying purification technologies if required. Water is my big thing, as you know, in this, not only the architecture, but in life in general. We can live without energy, but we can't live without water. And I don't know why it's not at the top of all the lists. Everything from the microplastics to the chemicals, pharmaceuticals, all the things going into our water systems. It's one of my big concerns, and one that I like to talk about on a regular basis, especially with students and trying to come up with better strategies. So I'm glad it is listed there. Utilize physiological and ergonomic knowledge in interior and furniture design. Pretty straightforward. Consider proportion, harmonic measure, order, and shape in design. I think from longevity, and I always design buildings not for the next 10, 20 years, but what is it going to do in 100 years from now? Having proper proportion and something that is beautiful, people will take care of it, because all buildings need to be taken care of. No matter what, if people abandon a building, it will fail and it will, you know, it will no longer cease to exist. So if you make things beautiful, I do strongly believe that people will take care of it, and generation after generation. So I do like that principle. They do talk a lot about natural and man-made electromagnetic radiation safety. It's one of the few environmental programs that actually look at EMR, but I won't get into too much detail today. But anyway, it's minimize indoor interference with vital cosmic and terrestrial radiation. 20, minimize man-made power system and radio frequency radiation exposure generated from within the building and from outside sources. Another one is avoid use of building materials that have elevated radioactivity levels. A lot of professionals and people in general don't realize that actually even something like granite, a granite countertop, can actually contain traces of radon. And when you seal it in with the sealants that are on those countertops, it is traceable and you can actually measure the systems. So if I have someone with a really extreme sensitivities, we will test any granite or recommend other alternatives for that, so you avoid that. But it doesn't mean to say that by having granite countertops, you're going to have radioactive levels. It's just something to be conscious of. Environmental protection, social responsibility, and energy efficiency. So construction materials, productions, and building processes shall provide for health and social well-being in every phase of the building's life cycle. I can't stress this enough. When I build buildings, 95 to 99% of our buildings are biodegradable. What happens at the end of its life? It goes back into the earth again, where it came from. That, I think, is something not necessarily discussed on the full level. Avoid the use of building materials that deplete irreplaceable natural resources or are being harvested in an unsustainable manner. I think we can all agree on that. Minimize energy consumption throughout the life of the building, utilizing climate-based and energy-efficient design, energy and water-saving technologies, and renewable energy. I love this one because it is the focus of my entire industry. And what I love is that it is important, but it's one of 25 environmental standards. And yeah, a big reason building biology started to resonate with me. Consider the embodied energy and environmental life cycle costs when choosing all materials used in construction. Where and how do those building materials come from, and where did they end up? So, accommodating a growing segment of the population. This is from Stats Canada. I believe in 2016 there was an allotment there. What is striking about multiple chemical sensitivities is its prevalence. The Canadian Community Health Survey shows prevalence figures of about 600,000 people in 2005, and in 2016, just over 1 million people are affected by MCS in Canada. What I've found interesting, if you look at our population, we have just under 40 million. That's about 1 in 40 Canadians supposedly would suffer from one form of chemical sensitivity or another. Now, our chemical exposure is across the board. Like we're exposed to so many different chemicals on so many different fronts. So I don't really get into that side of it. From the building perspective, the amount of off-gassing of materials is pretty intense. And I wouldn't have believed it until I had clients who can't go into a Home Depot without feeling really nauseous or sick. And it's not rare. Like when we started building our house, a lady down the street came and talked to us because she went on her own discovery to get better like 20 years prior, and she understood exactly why we were doing what we were doing. So it's resonated since going down this journey. The first thing we ask ourselves as building biologists is there a successful history of use? History is our best scientific study. So humans have always created durable shelter within the closed circuit of nature, no waste, no pollution, using natural materials at hand until very recently. Again, here we have a clay and straw. It was called wattle and daub at that point, filled in with a timber structure in Germany. It dates well over 800 years old and is still continuously inhabited. Yeah, there is a successful history of use. Mass wall construction, a balance of thermal mass and insulation equals maximum comfort and energy efficiency. It really is true. When you start adding a bit of mass, it can take in that sun. Two, when it gets hot outside, you can cool your house down just by leaving your windows open at night. It really does come down. I had a client come in about 2 summers ago. We had our windows open. It was about 11, 12 o'clock, and she had to put on her sweater. It was 35 degrees outside. Why she had a sweater, I don't know, but I guess she anticipated it was going to be chilly in the house. But it made her a believer, like, wow, this actually can work without air conditioning, which is something, I've tried very hard to do in buildings. So mass walls will actually help with that. Now, we'll get back to this hygric buffering capacity. The capacity of a wall system to store vapor without deterioration or loss of performance. What we see there, we see two photos, one of a steel structure and another of a log home. Now the log home, very similar to clay and straw, can take on a lot of moisture because those trees took on a lot of moisture during their life. And they won't deteriorate. So a log home actually works very similar to a clay and straw wall or any other type of mass wall. So the steel structure, once you have the insulation and everything else, you'll get about a 5-gallon capacity of moisture that can sit in those walls without rusting the studs and everything else. On the log home, you're at about 17,000-gallon capacity. Clay and straw would be closer to 100,000. Like the clay just can take on so much moisture. So the building envelope is our third skin. This is a building biology kind of analogy, I guess. The first skin would be, of course, our lovely skin that we have all on our bodies. It's pretty remarkable. When we get cold, we get these little bumps. They're called, or I know them as goosebumps. Those little bumps on our skin are actually air pockets, and they keep our body heat inside. So it acts as insulation. Now, when we overheat, our skin will actually perspire and let moisture out to cool down our body. So, you know, using that philosophy, all the different skins we're looking at work in the same way. Clothing would be your second skin. And you can understand if your clothing is not breathable, it can really make it uncomfortable. The third skin would be the building itself. And the whole idea of the building skin is its ability to dry out again. So the big thing with mass walls is to prevent the use of vapor barriers or a plastic layer. I love that photo. You could imagine being inside that plastic bag. The humidity would just eventually, especially on a hot day, would just start to collect and soak and, you know, drip down the edge of that bag. I mean, we wouldn't do this. Why do we do this? Vapor barriers cause a lot of failure in buildings. And it's one that I have come full circle on as an academic or even as a young architect. All we learned was to use these materials in conventional construction. When I saw the simplicity of a mass wall or clay and straw and how it went back, I had to step back. I took about an hour break and sat down and thought to myself and reflected upon my last 8, 10, 20 years of education on how to do things. I asked the guy who became one of my mentors, "Is that it?" And he looked at me and smiled and said, "Yeah, that's it. You mix clay and straw together, clay slurry, it's nice and wet, and you let it sit and you compact it in 2x4 wall systems. And that will do everything it needs to do from a wall system. You don't need the air barriers and vapor barriers because the wall itself acts as all of that. It understands moisture. And that's the one thing vapor barriers do, is that they try to prevent moisture from coming in. The alternative to it is that they keep moisture inside the wall. This is an excerpt from the Ontario Building Code. National Building Code 2 has something very similar. I've highlighted there OSB and plywood. This entire list here have perm ratings that are less than a certain rate to define them as vapor barriers. In our building codes, plywood and OSB are defined as vapor barriers, as are a lot of our plastic insulations. Now, we see this on most residential construction on the outside of walls. We put a vapor barrier and often very impermeable paint on the inside, and on the outside we have plywood and now often plastic insulations. So we have like 5, 6 layers of vapor barriers. And that's why we're seeing a lot of building failure inside of there, because we are not allowing moisture to come out. This is a photo, it's a sad photo, but a burst pipe was left unmanned for about, a good month or so, and it led to all sorts of mold damage inside this building. That's all the black spots are mold. And the mold grew on the paper backing of all that gypsum. It was the paper backing that allowed that mold to spread the way it did. So, I mean, technically we're building with a lot of materials that can't deal with moisture. So we've created a formula for failure. Lightweight synthetic building systems, moisture plus impermeable barriers, minus this hygroscopicity, the idea that building materials should know and understand water, give water the respect it deserves, equals building failures, health failures, and environmental failures. So if homes had labels, so let's look at some of these chemical sensitivities and see the chemicals that go into some of our things. It would be frightening. It took the food industry a very long time to get labels. The building industry will be, I don't know if it'll ever happen, but if we did, you would see a lot of crazy stuff in that list. How do we decide what makes a building healthy? Here we have foam insulation being applied in a spacesuit, and we have sheep wool insulation. How many of you knew that sheep wool could be used as an insulation? And sheep wool is the best insulation we have. It just, unfortunately, we're not processing it as such. New Zealand, you can go to like a Home Depot equivalent box store and pick up sheep wool insulation. It's wild. But sheep wool will contain, and we know this from clothing, 50% of its weight in moisture and still contain an R value. And as long as it can dry out again, it will maintain that moisture, or that R value. It'll never deteriorate. It is fire resistant, so it won't burn. It'll cinder a bit, but it's such a wonderful insulation, and we use it a lot in our buildings, especially around like window openings and anywhere that there's going to be moisture. The sheep wool will soak up that moisture and keep the window jambs and our windows dry. And that's very critical to, you know, the sustainability of a building. Foam insulation, it sticks to everything, and if you're ever going to do a renovation in the future, it's really tricky to do. It works initially. I'd say from a long-term perspective, it does have issues. And of course, there's the off-gassing. A lot of my clients couldn't even live for 20 minutes in a house with spray foam. There is significant off-gassing. Yeah. Well, I mean, the spacesuit might give you the first indication. So staying informed in a swiftly moving target. We see here crazy amount of different certifications and all sorts of different things on what chemicals should be allowed and how, you know, difficult they are to deal with. So how much do we really, or how much do we know? We really don't know very much. The EPA in the US in 1976 grandfathered in 62,000 chemicals into their industry. The good news is that the EPA is now going to test them. So, I mean, to test 62,000 base chemicals, I mean, we're talking thousands of years. It really would be tough. And that's testing one chemical and its problematic causes to one individual, right, or a series of individuals. It doesn't take into account all of the other things. 1 plus 1, what does that equal? If you have chlorics and ammonia, if you have most like Windex or window cleaners tend to have a bit of ammonia in it. Most of our, you know, chloride bleach is still sold in stores, and they're stored right beside one another. And often in our homes we store them. You put them together and you get lethal gases coming from it. Now, what if we look at 1 plus 1,000? Any of those different combinations, there's no way of knowing what the indication and what the consequences would be of the chemical sensitivities or the chemical exposures inside of a building. So, and we don't have full disclosure. An SDS, I don't know how many know what an SDS is. You need an SDS form when you're working with materials on a job site. And it's just to go through safety precautions for how to treat and deal with that material. So there's health effects of trade secret ingredients. Trade secret ingredients do not have to be on an SDS sheet, which I find crazy. Hazardous ingredients less than 1%, which could be a lot. Carcinogens less than 0.01%. Inert ingredients, PEL and TLV level untested and based on single exposure and set by industry obtainability. And health effects don't accurately portray long-term multiple exposures, which is very true. So if you're working in a manufacturing shop and you're being constantly exposed to the same thing day in and day out, that will never be shown on an SDS because there are no tests to show what that would do. So it is a tricky thing in the building industry, and why, you know, we've kind of developed ways to look at the individual ingredients. And in the end, I don't do that much of it because a lot of our materials are natural and they don't contain any of this stuff. So making sense of chemicals for a non-chemist, we have accessed Pandora's box. The 85,000 plus man-made chemicals approved for commerce derive from roughly 88 of the elements found on the periodic table. So nature, the gold standard, with a 5 billion year track record. All of the functions and services delivered by living systems found in nature in our environment are the result of these 12 chemicals in the periodic table. It's wild, 12. But yet we've introduced all these other ones. And yeah, even the building industry, you focus on those 12 and the buildings will last a lot longer. Oh. So 6 classes approach, I'm not going to say it. If you do have time at any point in time, look at 6 classes. It is a very, very good website that really looks at the different types of classes. So there, yeah, there's about 5 minutes left. So again, you know, when we're using chemicals, at what cost and to whom? So here you see a natural building going back into the earth again. It's starting to biodegrade, and once its lifespan is done, it goes back into the earth. Most of our other buildings end up in landfills. Has anyone heard of the Pacific trash vortex? Yeah, it's gigantic. It's twice the size of Texas and looks like this. I'm going to go through, I want to show you some photos of our house. So applying building biology principles. We were recently published in La Maison. There's a good article in there that I wrote with the editor from La Maison. This was the fall edition, and yeah, if you have a chance, there are some good insights into there. So toxic-free, first, do no harm. I try to use natural materials and things without the chemicals. That way I don't have to bother vetting it. A home will be successful to the degree that natural, unprocessed building materials are used to create it. This is our house. It is clay and straw. It is the sprouting that occurred from a lot of our wall panels. This is a picture during construction of our house. It is located near the experimental farm area in Ottawa. This is a picture of our wall 3 years after we installed it. I left the walls exposed for about 3 seasons to see exactly what it's doing. And I was stunned. The clay straw looked like the day we put it in. So natural self-regulation of humidity, ionization, and acoustics using hygroscopic building materials and finishes. That's a photo of my daughter. We have an earthen floor, clay walls, and a timber structure inside. Natural climate control, we have lots of operable windows, like I say. Natural interior finishes. This is a Sugi Shubon, so burnt wood on the backdrop of our kitchen. We also use soapstone countertops just to avoid the use of a lot of preservatives or sealants on the countertops. Thermal storage capacity. This is a photo of our masonry heater in our main living space. I'll go through it very quickly. I took some infrared photos. You can see some of the temperatures here. This is after the fire goes out. It's at about 108 degrees Celsius in front. After 3 hours after the fire goes out, it's 120 degrees Celsius, which is wild. It just gets warmer and warmer, and then eventually cools down again. What I also find interesting with this is that it actually increases the wall temperature. That wall was 5 degrees warmer, and when these were taken at 6 a.m. in the morning. So the wall absorbed a lot of the heat from that masonry heater and got much hotter than the room temperature inside. So it was actually storing it and helping us. Yeah. Electromagnetic radiation, we do talk a lot about that, especially with clients who have sensitivities. Natural daylight, I can't stress this enough, it's free. We should be stressing as much natural daylight as possible. And a big thing I try to stress with all my clients is bringing them outside. Let's design some exterior spaces, because exterior spaces that are well designed will be used a lot more than those interior spaces and cost a fraction of the cost. So I do emphasize a lot on exterior spaces. Yeah. Natural daylight, a few more photos of our 2-story space. Lighting inside. Lighting is very big for me. In residential construction, I've completely taken away from the LED side of things and went back to incandescent. And it's largely for the light quality. We get a little bit of energy savings on the LED side, but the quality of light is night and day. And in the evenings, when you need to calm down, the incandescents are like candlelight. It really does help. But most people, again, want to look at those energy savings. But if you look at the energy heat you get from the incandescent, it warms you up too. So there are arguments on both sides. Color and pattern in accordance with nature. That's my son running around our floors. I want to end with Taos Pueblo. Does anyone know Taos Pueblo? It's like it'd be a First Nation in the U.S. Near Santa Fe, New Mexico. So it's up in the mountains, about 9,000 feet above sea level. The photos you see here are photos of it, and it dates back well over 1,000 years. So it's a heritage site, World Heritage. Taos elevation is about 9,000 feet above sea level, so it does get very cold. It's over 1,000 years old, and it has been continuously inhabited. It is the oldest continuously inhabited community or buildings in North America. It is adobe construction, so clay and straw, a mixture of clay, water, and straw poured into forms and sun-dried bricks. It's clay plaster exterior, and no plastics in these buildings. Taos Pueblo. And when you see it in person, it's hard to argue with something that's lasted 1,000 years and still maintains the structure and everything else it was intended to do. Yeah. Thank you for the presentation. Questions, or do we have time for questions? Okay. Okay, sounds good. Bathroom ventilation? Oh, like with the fact that clay brings in the humidity. If you wanted to use like a cork ceiling or some form of wood, that's a very simple way of doing it. You could also deal with clay plasters. And if you put a bit of clay plaster inside that, it would soak up a lot of that moisture and it would reduce your humidity, hence the mold or any kind of other growth that would be coming there. But people have introduced like cork ceilings. You need a lot of it. Or like a wood ceiling, like a cedar ceiling would help. It wouldn't take all of it away, but it would help immensely. Yeah. No, like in our bathroom, you won't need a fan because there's no humidity. And we open our windows pretty regularly. Like they're open almost 24/7, 5-6 months of the year. And we can do that because we have so much mass. The sun's warming it up and everything else, right? It's actually quite comfortable consistent way of not only cooling and heating, but also dealing with humidity. Yeah. Yeah. Natural materials, wood and clay do it very well for moisture. Yeah. Other questions? Yes. We have a 7,000 square foot house planned in Wakefield next, in 2023. So yeah, we've developed, I could see, from an architect's point of view, I don't believe we should be building more than 3-4 stories in construction height, just for the maintenance of it. But yeah, you could get to 3-4 stories, no problem. I find our high rises, the biggest thing they're going to lack in 20, 30 years from now, and we're seeing it already in older buildings, is the building failure. And then how do you repair the entire skin of a 30-story building? It's really difficult to do. So, you know, outside now? Or we're good for review? It's all good. Any other questions? Yes. This is why I started a design build company. In the future, probably, you know, a few years from now, I will be teaching other people. I'll probably teach less at Algonquin and really focus on teaching more builders how to do this, as more and more people need to be looking at. And there's a lot of good natural building systems, like hempcrete's a common one in Quebec, not recognized at all in the city, and they don't have enough testing really to get in the city yet, but it is a good wall system. Straw bale, clay straw, rammed earth, adobe. And they're all stuff you can do. I did an adobe wall in the inside. We have a wood stove as well, a wood cooker, and that heats remarkably well. It stores a lot of the heat, and in the summer, it keeps the house cooler, which is pretty remarkable. We don't get much because it's slab on grade. I try not to build with basements. I will if clients want them. But if you take the basement out of the equation, there's no humidity because there's so much airflow when you open your windows. Yeah, there's not much at all from that perspective. And we have, you know, systems for radon and stuff, so there's no radon coming up through the slabs. Oh, yeah. Yeah, no, for sure. A finished basement's more expensive than a second story. No one believes me when I tell them it until I show them where the costs are going. Because I do really detailed cost estimates, because when I got into building, I realized how quick projects can go over budget. So my big thing is, well, things need to be within whatever budget a client wants. So with that, yeah, no, for sure. A second story is always going to be cheaper than a finished basement. And you'll have ample light and all the other good stuff. Yeah. So, yeah, we have 2-3 2x4 walls, and then we have, it's a SonoClimate product, so it's a fiber board we put in the inside. We prefab all our buildings, so the SonoClimate acts as a bit of additional insulation, but it also acts as formwork when we're putting the walls together. And I did that largely because you would still have a pretty good R value with a thick clay straw wall that's 12 inches thick. It would pass all our energy codes. The trick is to dry that out. Like I say, when you put that much water inside, it does take a long time. So, you know, when you split it up and have smaller wall systems on each side, you tend to prevent, or you just slow down the drying process so that you don't have as much of that lead time. And we have a continuous insulation of about an R15 in the middle, and then each of the clay straw have about an R8 in total. So an R8. So there's a continuous of R15 with an R8 on either, or R4 on the other side. What you don't get into that equation is the mass and how much that does for heating and cooling. Yeah. And humidity. Yes. Well, thank you, everyone. That was great. I'll be outside if you want to ask me any other questions. We'll talk outside. Yeah, yeah. I know they're eager.